Hey everyone, welcome to Cleared for Takeoff. Cleared for Takeoff is a student run interview series featuring aerospace professors, professionals, and students, focused on sharing real experiences in research, academics, and industry. It aims to give high school students clear, practical insight into pathways and careers in aerospace engineering. Today, we're joined by Dr. Oliver Jia-Richards, an assistant professor of aerospace engineering at the University of Michigan, whose research focuses on electric propulsion and spaceflight mechanics, such as designing thumbnail-sized thrusters and finding clever ways to measure and control the tiny forces that move spacecraft through space. Thanks so much for joining us, and welcome to Clear for Takeoff.
Thanks for having me.
For our first question, you stayed at MIT all the way from undergrad through your doctorate. Then you did a postdoc at Cornell before starting your own lab at Michigan. What surprised you most along the way at each of these stops, and what were your main takeaways from each of these steps in your journey?
So it's a tough question. I guess I'd say initially I don't think there was anything that was too surprising along the way. But I think to the second part of your question about the main takeaways is really my journey through that, and the reason why I stayed at MIT the whole time was just going with the opportunities that were available to me and taking opportunities that seemed interesting and things that I could learn from. And so when I started at MIT as an undergrad, they have a very strong culture of undergraduate research. They have an undergraduate research opportunities program.
Mm.
And so when I got there, I knew I was interested in space propulsion. And so I reached out to the faculty member that works in space propulsion and said, I'm a incoming first year student. It'd be great to work in a lab. And the opportunity that I got at the time was not what I would now consider necessarily research, right? But an opportunity to work with a graduate student in the lab and to help them. And in particular, during high school, I had done a lot of robotics
Mm.
work and particularly machining. And so I said, I can do machining. I'll machine anything for you. And so a lot of my initial tasks were just making things. They weren't really doing research. And
Uh,
so using those skills to sort of help the grad student I was working with. And then I just followed that. And so I stayed in that lab. I did bounce around through a couple of labs during my undergraduate time to explore different opportunities, see what other things might be interesting. I eventually went back and then stayed there for my grad school, went to do a short postdoc with someone else who had been in the lab and then had started a lab at Cornell, and then continued on to the University of Michigan.
Thank you.
So for our next question, when people think of rocket engines, they picture something huge and fiery. But you work on electrospray thrusters, devices that are smaller than a thumbnail that push a spacecraft by flinging out charged particles instead of burning fuel. What's actually happening inside one, and what are they good for that a big engine is not?
Sure. So I think the way to think about all space propulsion systems, whether or not we're talking about what you'd say is a traditional rocket or these electrospray systems, is that they're all energy conversion devices. So all they're doing is they're taking some form of energy, whether that be chemical energy stored in the bonds of whatever propellant you're using, or potentially electrical energy that you're providing from the sun in the case of electric propulsion, and you're converting that energy into directed kinetic energy of your propellant. And you're just exhausting it out the back of your thruster and then generating thrust from the reactionary force. And so if you think of it that way, then really the separation between these devices is just how do you manage to put that energy into the system. And so for a chemical engine, you are limited by the energy stored in the, the chemical bonds, right? And so you're using combustion to get that energy. And so for a rocket, right, then you can get energy, more energy, but just putting in more propellant. But if you think about the energy per propellant that's available to you, it's inherently limited by the energy in the bonds. Electric propulsion, which is what electrospray sits under, you're taking electrical energy, typically generated through solar panels, taking it from the sun, or potentially even some futuristic systems consider the use of nuclear reactors. You're taking electric energy, and then you're putting that into propellant, where you have a charged propellant, and then you're, in most cases, accelerating it by an electric field. And so in that sense, what you can see is that the energy that you're putting in is no longer limited by the propellant that you have. It's limited by how much energy you can collect from the sun.
Yeah.
And so it allows you to put a lot more energy into an individual particle, per se, and accelerate it to a much higher speed. which makes them much, much more efficient. But at the same time, you still have to provide that energy. And so if you look at a lot of spacecraft that have electric propulsion systems on board, they have these very large solar panels because you need to collect a lot of energy in order to provide the energy required to accelerate the particles. So really that's the main thing. They're both systems that are just taking some form of energy and making it into directed kinetic energy of the plume. In the chemical case, you can get these very large engines that are processing a lot of propellant and are produce a lot of thrust, but you're limited in terms of how much energy you have to put in. And then on the electric side, in theory, for a single particle, you can put as much energy as you want into it, but you have to provide that energy from somewhere. And so it becomes a lot more tricky to produce a lot of throughput in terms of the mass.
Staying on topic with electrospray spray thrusters, a lot of your work is about measuring how much push a thruster makes by watching how the spacecraft's orbit slows down rather than measuring it directly. Why is the thrust from these tiny engines so hard to measure that you have to work backwards from how the spacecraft moves?
Sure. So the way that we measure thrust, there's two general ways that we measure the the thrust produced by a propulsion system. And you generally classify those as either direct or indirect. And so in the direct class, what we're looking for are ways of measuring thrust that are you're looking at the direct influence of that thrust on a system.
Hmm.
And so a lot of ways that propulsion systems, not only electric propulsion systems, but chemical propulsion systems or even aircraft engines are characterized are through these approaches, where typically what you would have is a force balance sitting on the Earth, which is just a spring mass system. And so your thruster pushes on the spring, you measure the compression of the spring, right? And that tells you how much force it produced. And so
Hmm.
you're measuring the direct impact of that force on the system. Now, in space, that's a lot trickier to do than it is to do on the ground. But when we do it with the direct approach in space, what we're looking at is not the impact of the force on, say, compressing a spring, but rather the impact that the force has on the spacecraft's orbit. But it's the exact same idea. And so that's why we use that approach in space, is it's just a much more easily measurable impact of the system, and you can take the measurements over much, much longer periods of time.
Hmm.
Now, the other class of way that you can measure thrust is these indirect approaches. And there, what you're doing is you're trying to measure the thrust, as it says, indirectly by trying to infer it from other characteristics of the system, but not the direct influence of the thrust. And so, for instance, with an electric propulsion device, we have a lot of charged particles. We're accelerating those charged particles. The way you might infer the thrust is by measuring the current, for instance, that's leaving the thruster. And there you have to apply some assumptions, right? So you say, well, I measure this type of current. I know what particle I'm accelerating. I know how much I've accelerated it by. So if that many particles are leaving my system, that should give me an estimate of the thrust, but you're not measuring the direct impact of it. And so that's very frequently used for these small systems because it's very tricky to measure the very, very small thrust produced by these electrospray thrusters, which are typically, micronewtons or so.
Hmm.
To give a sense, that's roughly equivalent in force to, a hair, right? That you might have on your finger. So it's very tricky to actually measure that. And so a lot of people use these indirect approaches because current's a lot more accessible of a measurement, but they're not as accurate. You have to apply a lot of assumptions to how the device is working. And so that's really why we've been pursuing these direct approaches, is saying, well, this thrust is so small, it takes a long time for it to have any appreciable impact on a system. And so by just monitoring the orbit over an extended period of time, we can still get an estimate, right? And we can use that to calibrate the indirect thrust approaches that people commonly use.
Hmm. Thank you.
Thank you. So for our next question, we saw that you came up with this idea of staging electrospray thrusters, which is essentially jettisoning worn out ones to expose fresh ones, the same way a rocket drops its stages on the way up. So we were wondering what problem made that necessary, and how does it let a satellite the size of a shoebox reach deep space?
Sure. So I guess I'll start saying it's not my idea. It was my advisor's idea. And actually this goes back to your first question of sort of, how I followed my path. And essentially, I guess the story there is I was finishing my undergraduate degree. I was thinking about grad school and where I wanted to go. And the faculty member who I'd been working with for my undergraduate degree happened to get this NASA project which was about this staging concept. And so it was very well timed. I finished my undergraduate degree, and then the next day I showed up and I was a graduate student working on this project. So certainly not my idea. I happened to just work on it and put together the initial concepts for how such a system would look like. But the essential point of the system was that with these electrospray thrusters, they're very small, they're nice and compact, which is a very useful quality. So it's actually very hard to take a lot of electric propulsion systems and scale them down to these kinds of scales.
Mhm.
And so electric spray propulsion is one way of doing that. But the challenge still remains that when you try to scale these systems down to these levels, oftentimes what suffers is their lifetime. And so you're able to produce a thruster that is, as you said, thumbnail sized, but they don't last long enough to do, for instance, a deep space mission as you might want. So to give you a sense, right, the lifetime of the thruster might be a few hundred hours. You need it to operate for months or even potentially a year to accomplish these missions.
Yeah.
And so the essential idea was to say that, given the current state of technology of the lifetime these thrusters had, of course, people were working on how to improve their lifetime. But taking a given stage of their technology in a given lifetime, one way that you could improve the overall lifetime of a whole propulsion system is to leverage the small scale of the thrusters. And instead of just having one set of them, just carry a whole bunch of them. And because they're so small, they're fairly easy to stack. And then as one set reaches its lifetime, you just eject it, and then you have another one that's available to you. And so it's sort of a hack, right, to say that we have a current technology, it has its lifetime limit. While we work on improving the lifetime, here's an alternative way we can get a whole system to have a better lifetime using the current technology. And so from there, we can go from these sort of few 100-hour lifetimes. You can, in theory, put as many of these as you want, and that extends your lifetime sort of
Yeah.
linearly, depending on how many stages you want. And that's what would enable you to get the lifetimes required for these deep space missions.
Thank you.
So for our next question, you modeled a disc-shaped rover that uses the natural electric charge on the surface of the moon or an asteroid to actually hover above the ground with almost no fuel. Where did the idea come from, and how close is something like that to being real and coming into reality?
So I don't know exactly where the idea started, but it was an idea that my advisor and I started looking at in grad school, um, looking at alternative ways that you can achieve mobility on small planetary bodies, up to the moon, but mostly considering small asteroids, leveraging these electrospray thrusters. So if we go back to the discussion of the different kinds of propulsion system, at its core, electrostatic propulsion systems are just particle accelerators. They take charged particles and they accelerate them and they produce this ion beam. And normally you would use that to produce thrust through Newton's third law. But you also have this handy ion beam that you could use for other things. And one of the main concerns people have with electric propulsion is this idea of spacecraft charging. So we have this ion beam that we're accelerating. It's a whole bunch of positive ions. If you don't do anything, then your spacecraft is going to have this deficit of positive ions on board, and so it'll be negatively charged, and bad things happen essentially. So that'll attract the ion beam back, reducing your thrust, could cause arcing events on the spacecraft, and so on. And so if you look at a lot of electric propulsion systems, what they'll have is this neutralizer which is just emitting electrons. It's not contributing to the thrust at all, but it's emitting those electrons to keep the spacecraft charge neutral. The idea we had was to say, well, what if you don't keep the spacecraft neutral or the vehicle neutral, and instead try to actually leverage the charging that occurs? And so we took the ion beam and we essentially said, let's imagine this disc-shaped robot as you described it. And if we just emit these ions, then it'll charge positively or negatively, depending on the polarity of ions you emit. And if we let that ion beam impinge on a surface, then it'll deposit that charge on the surface and also charge the surface electrically. And so by playing with your ability to charge the vehicle and playing with your ability to charge the surface, you can produce these electric forces that we found to actually be fairly significant. Enough to, do this levitation as you suggested, but also you could anchor a vehicle to the surface. And actually, that's one of the tougher challenges with exploring these small bodies is how do you actually stay on this object that
Mhm.
has so little gravity that you don't really want to sit on it, right? Or it's very difficult to sit on it.
Mhm.
So the whole idea was to take these propulsion systems, leverage in this alternative way. Again, I'm not quite sure exactly where the idea started, but we ran with it, and we just in that study did some basic back of envelope analyses, as well as some experimental proof of concepts to show that you actually do produce this force and that it can be appreciable enough to enable levitation or anchoring, depending on what you want to do.
My next question was about some of your newer work, which is about small spacecraft that can inspect or service bigger structures, like a possible lunar station, and react on their own if a thruster starts to fail mid-task. Why does a spacecraft need to make these decisions itself instead of waiting for instructions from a user on Earth?
Yeah, so that's a great question. And the answer to that is it really depends on the scenario that you're considering. And so if we think about a lot of spacecraft and how they're operated these days, we would describe that as open loop. Basically, there's an operator on the ground, they send a command to the spacecraft and it does it. Right?
Hmm.
And that's quite effective at allowing us to achieve a lot of things. But there are certain missions that people might want to accomplish that it becomes quite tricky to actually continue to operate that way. And one a couple of examples that are particularly important for that are cases where the spacecraft needs to be able to respond to dynamic mission conditions very quickly, right? And so you can imagine that if we have the spacecraft inspecting something around the moon and something goes wrong, you don't necessarily want to have to wait for the operator to figure out something's going on, figure out how to resolve it, and then tell the spacecraft what to do. And by that time, it might have already crashed into the station or whatever object it's operating around. Or the other way that people consider this is if we have missions to the outer planets, right? So the icy giants, then the light time delay is so long that
Hmm.
something could have already happened to your spacecraft and you would never have known. And there's just not an opportunity for the operator to actually make the decision.
Yeah.
And
Yeah.
so for those reasons, it's quite handy to provide the spacecraft with the ability to make its own decisions, right? For that, as well as a whole bunch of other reasons, such as just minimizing operator workload. And so the idea here was to say, if we want these spacecraft to operate autonomously, then people have developed a lot of methods for how to have spacecraft or other robots plan trajectories on their own, given, a model of how they will work. But if you look at sort of the history of small spacecraft in particular, they have very frequently anomalies that can occur on board. And in particular, the one we were considering was anomalies in the propulsion system. So the actuators might degrade or just completely fail.
Hmm.
And this means that when the spacecraft tries to plan its trajectory and execute it, it won't actually do what it's intended to do, right? Now, in the open loop system, the operator would notice the spacecraft's not doing quite what it's supposed to be doing, figure out a fix and go back, right? But that might take too long in these scenarios. So the whole objective of our project was to say, how do we enable the spacecraft to act intelligently on its own in these scenarios and figure out what's wrong, or maybe not diagnose exactly what's wrong, but figure out enough to know how to act in a way that it will not cause damage, could potentially still continue its mission or other objectives, right? And so the whole project, we took some ideas from reinforcement learning, which is a very effective way of having things learn about their environment and act intelligently in it, and use some ideas from reinforcement learning to test whether or not these spacecraft could actually accomplish this. That's the idea of the project. We partnered with NASA JPL for this project. It was funded by a NASA program called University Small Sat Technology Partnership Program, and so it was my team along with a team at JPL where we had this algorithm development that we were working on at UM, and then JPL has a very nice flat floor hardware facility, and they also helped out with a lot of the algorithm development as well. And we were able to do hardware testing at JPL and demonstrate it on their flat floor facility and show that, with these approaches, you can actually enable spacecraft to act even though, one or even more of their thrusters have failed. And in other cases, if you use traditional controllers, the spacecraft just flies off. It has no clue what to do in that scenario.
Thank you. That's a great story. Thank you.
So for our next question, we saw that you co-taught a class on cleaning up space debris alongside law students, not just engineers. So why does a problem that sounds purely technical end up tangled in regulations and economics too?
Well, that's just kind of the reality of all engineering systems, right? And I think, particularly when we teach traditional engineering courses and we want to do our engineering research, we like to just focus on the technical aspects of it. But the reality is, if we have a system, it eventually has to interact with society in some way, right? And we can't just do whatever we want to do. And so the specific aspect here is looking at space debris. So satellites or other objects that we've put in space that are no longer serving a useful function to us, right? So you can
Mhm.
consider a rocket body, for instance. That's already launched this object, but now it's there. And the specific aspect here is we can't just keep putting things up in space. Eventually, it just gets too cluttered, and then we can't effectively operate. But there's not really an incentive, if you just consider it from a technical aspect, for a satellite operator or a launch vehicle operator to bring their object back down, right? Because
Yeah.
if you imagine I have a satellite that's accomplishing a mission, if I want to actually deorbit it, that means I need to now have a propulsion system on board. I need to dedicate mass and volume to propellant, and that's taking away from payload mass, right? So it's directly decreasing the commercial viability of that satellite. So if we didn't have any regulations or policies, no one would do anything, right? Because it makes no sense from a commercial perspective or technical perspective to do that.
Yeah.
And so these regulatory systems are put in place to encourage that, right? And sometimes it's a bit more forceful. It says, you have to deorbit it within 5 years is now the rule, or we'll fine you. And there have been places that companies that have been fined based on that. And sometimes there are incentives put in place to say, well, if you deorbit it, maybe you'll get some benefit, right, out of having done that. And so the whole idea of this class that was co-taught by myself as well as a faculty member in the UM Law School was to look at this problem and look at both sides and specifically get law students and engineering students in the same room to talk about this. And so I think it was a very interesting class as someone myself who never has touched the regulatory side and mostly stayed on the engineering side. It was very interesting to learn about the considerations a law, graduate might think about as they're looking at this problem. And I
Mhm.
think it was really useful for the law students as well to look at, they can't just put any regulation in place. It has to be technically feasible, right? You can't request, for instance, that a satellite, the moment it's done with its mission, deorbit. Things take time. You can't just deorbit it instantly. And you also have to consider that if you place too heavy a restriction in place, it might just be impossible for people to meet without, you know, ruining the economic viability of the mission they're trying to accomplish.
Yeah.
So I think it was very useful for both sides of the two schools, if you put it that way, to think about these problems together and look at solutions that consider both sides of the problem and try to meet, somewhere in the middle.
Yeah, that sounds like a really interesting course. And I had a quick follow-up question. So, are there any like organizations, like international organizations or like treaties in place, like specifically like deal with that kind of problem? Because I know it takes like a lot of compromising from like a lot of different entities and stuff. So,
So I might have to direct you to those in the law school to really get a lot of detail about that. I do know there are some, but I, from my understanding at least, the reality is that space is not that regulated. And in most cases, you can kind of just do whatever you want, right? There are some, right? And so in particular, there's the FCC. I honestly don't know what it stands for at this moment, um, but I um, but I believe is related to communications, which does place this 5-year rule on a satellite. And
uh,
so that is one of those more forceful aspects. And I believe you may want to check me on this. Or the rule is that if you want to be able to operate communications in the US market, you need to abide by this rule.
uh
Yeah.
Thank you. I'll check. I'll make sure to check it out after this.
Yeah.
So for our next question, a lot of high schoolers into aerospace picture themselves designing rockets and planes and something of that sort. Your work is more about math, the controls, and the estimation, the intelligence that figures out what a vehicle is doing. What would you say to a student who doesn't see themselves in the traditional build the airframe mold?
Well, I'd say I think aerospace engineering is a good discipline in that there are opportunities for people to do a lot of different things. And I would actually say I myself am someone who got into aerospace engineering without really being that interested in a lot of these vehicles. I can't really tell you the difference between a lot of planes. And so there are a lot of faculty, those particularly on the aeronautics side, who can tell, the plane by the sound of the engine, right? Or take a look at a plane and know exactly what it's doing, and I have no clue. And okay, I knew a little bit more about the space side. I found rockets to be cool, but I couldn't really have told you much about, the history of space. And I think one challenge that students can sometimes face is that they maybe don't have so much of an interest in, say, aviation history or space history. There are people who pursue aerospace engineering because of that passion, and that's great. And then the students that come in that don't necessarily have that don't see themselves in those people and wonder maybe if this is the right thing. And I would tell you if you're interested in it, it's certainly something that I think is worth pursuing. And there are lots of different ways that people can get involved in aerospace engineering. The math is certainly part of it. If you pursue controls, you're going to be doing a lot of math, right? If you pursue a lot of the sort of fluid dynamics side, you pursue a lot of the structural side, you're going to be doing a lot of math as well. Well, it's impossible to avoid the math, but there are also aspects that you can work on that maybe don't have so much of a math emphasis, right? And so, for instance, bioastronautics is an aspect of astronautical engineering focusing on humans in space or just generally biological systems in space, right? And there's still math under the hood, right? But it's not the same sort of uh, requirement of math or overblown amount of math that you might see in a control system.
Yeah.
So I'd say if you just have any interest in aerospace systems, then I think it's a worthwhile field to go into. And looking back at my own story, I basically went into aerospace engineering because I thought it was interesting. I thought it was cool. You learn a lot of the same engineering techniques that you would in other fields, particularly mechanical engineering, but you learn them in the context of an aerospace system. I think that can be very useful for people who are interested in those systems because being able to see the math in the context of the system you're interested in helps a lot in terms of the learning. But also, I would just say that, if you don't necessarily have the same passion as a lot of the students that are there, that's completely fine. I didn't have it, and I ended up okay, right? And also, just because there are certain classes that you may not, you know, be as good at, I was never good at fluids, and I really could not do structures very well. But there are other things that you can do. And so I think aerospace provides an opportunity for you to explore different areas and try out different things. And I think there's probably one there for you if you have an interest in aerospace systems.
And just a follow-up question, I know you were mentioning specific classes. Was there like one or two maybe specific classes that really like piqued your interest in this field and like you knew that you wanted to kind of dive deeper into that field?
When I started, I definitely had an interest in propulsion. That was sort of why I started going into aerospace, is I thought propulsion was interesting. And I didn't, when I started, my conception of propulsion was these traditional rockets, right? You look at the launch vehicles in particular. And just by the nature of the research I started with in my first year, right, and being exposed to these electric propulsion systems, I would say that is probably what started getting me very interested. The beginning is looking at this completely different way of doing propulsion. I'd done E&M in high school physics, right? And sort of, well, that's kind of interesting. You can have these particles move around, you can analyze circuits, right? But that's kind of the extent you get to. But then being able to see it applied in these systems in a way that I didn't even think was possible when I started was quite interesting. And then along the way, I think treating the undergraduate curriculum as a way to explore and try different things, you end up discovering areas that you maybe didn't even think of, but end up enjoying. And one of those areas for me was controls. So I went in thinking I was going to do propulsion systems. And in my first year, I decided, well, I'm going to do electric propulsion systems because that's what I've been exposed to now in my research. And then I took a controls class and I said, this is kind of interesting. And so that kind of shaped the direction I went. I got very interested in controls and dynamics. I still kept my interest in electric propulsion, of course. And you can kind of see now that that's shaped where my research group has gone now, right? And so we're very interested in what I would just call space mobility. And so looking at how do these propulsion systems work, so you can kind of see that influence of I had an interest in propulsion. I did a lot of research in electric propulsion as an undergrad. And then also the dynamics, the astrodynamics component of it, and how do we actually use these systems? You can
Hmm.
sort of see the influence there of when I took that controls class, and I thought it was an interesting avenue to go down.
Thank you.
For my final question, I wanted to ask if a student watching this is genuinely curious about breaking into academia or space or propulsion, what's one concrete thing they could do to start exploring? You mentioned your advisor, high school robotics, and your time at top universities. Which of these had the greatest impact, and how can our viewers find these influential environments and events?
I think that's probably the hardest question because it's very person dependent.
Hmm.
I have my story, I have the avenue I took. That's worked for me. It will not work for everyone, right? And
Hmm.
I know even among most of my colleagues, we have different ways that we got to where we are now. So that can be one advantage in that there are many different paths to get to wherever you want to go.
Hmm.
That, of course, presents the challenge of it's very hard to give advice, right, about exactly what to do.
Hmm.
My my main advice would be to just continue taking opportunities as they come and following the opportunities that you enjoy, right? I think that's really, if I look back at what I did, I got lucky a lot, right? Getting into MIT was luck. I didn't do anything special for that. That's a lottery in some sense. And
Hmm.
so I got lucky there, and I now have the opportunity. I had the opportunity to work with my advisor during undergraduate research. And just taking those opportunities and pursuing them led me to where I went, and I didn't have a plan at all for where I would go. If I think back, even when I was doing my master's degree, I was still on the fence of, am I just going to complete this and go into industry, or maybe I'll continue and do my PhD. And it wasn't really until, I got a year into my master's, I thought maybe I'll do the PhD. And then I was doing the PhD and I thought, well, this is interesting, but maybe I'll still go on and work at JPL or do something else after. And it wasn't until maybe the last year and a half, and I thought maybe I should do academia, right? This
Hmm.
is this is interesting. And so from that, right, it was really just going with the things that I got fulfillment out of, what I enjoyed doing, and taking the opportunities as they arrived. And to me, that was what led me down my path. To me, that's the advice I would give. But also with the caveat, right, it's sometimes hard to get these opportunities. So when they arrive, take them and prepare yourself for, getting more opportunities by doing your best when you get that opportunity and chance.
Of course, thank you.
Thank you. Thank you so much for your time today. We really appreciate it.
Yeah. Thanks for having
Thank
me.
you.
And I just wanted to make sure we usually post these interviews like on our social media channels, like our YouTube or our Instagram. I just wanted to make sure that was all right with you.
Yep, that's fine with me.
All right. Thank you so
Thank you
much for
so
your time.
much.
Have a great
Thank
one.
you.
Thank
Have a
you.
great summer.
Thanks, you too.
Thanks.